Hello everyone, today we're doing a very brief video on heat transfer. So this is a very important concept that we have in our booklets. We are now on page uh, 21 by my count. I don't think these pages are numbered. Okay, so oh yeah, they are, page 21. So on page 21 of your booklets, we have a fill-in here that is on how energy is transferred, how it moves. This is a really important concept in weather because a lot of the reason that we have weather patterns is simply because of the movement of energy and the way that energy moves. So there's a couple of different methods that energy can undergo to move around. Well, the first type is conduction. So this one is somewhat important in weather, but let's talk about this. So in conduction, this is where heat moves from one place to another without the molecules actually changing location. Instead, fast vibrating molecules in a hot place simply bump into slower moving molecules in a cooler area next to them. This process passes the heat energy along to the slower molecules, making them move faster too. So there's no intermixing of chemicals here. There's no intermixing of matter. You have a hot piece of matter and it's touching a cold piece of matter, and in that zone where the two connect with each other, the energy is passed between those two. So wherever that hot piece of matter is touching in physical contact with the colder piece of matter, we get a transfer of energy, and that's conduction. So for example, quickly moving molecules in the stove element will bump the slow moving molecules in the cooler frying pan. That speeds up the molecules in the frying pan, and so the frying pan becomes hot as well. That heat energy can even be transferred to the bread that you put on top of it. So in this picture, we have a piece of bread there, or a sandwich being made on the pan. So at the interface, that's where the molecules of the bread are touching the hot pan, there might be some conduction happening there as well. And that's one of the reasons that the bread gets burned at the very edge where it's touching, because there's extra energy coming into the food from that area. So so here's a picture of that. You can see the fast-moving particles. So these are the fast-moving particles here. They are moving very quickly. We've given them energy through electricity and through resistance, so that's a different process. But then at the interface where these hot particles are interacting with these cold particles, there is going to be an energy transfer. And so this passes off some energy as kinetic energy, just like in the car crashes we studied before, where there's this sort of transfer of momentum. That's a very similar idea. We have a transfer of energy from the fast-moving stovetop particles to the pan, and we can always think that this is why the stovetop has to actually be hotter than the pan, because you're only going to be able to transfer a small amount of that energy through this conduction. In terms of weather, conduction is important because this is largely how the atmosphere gets heated. The warm earth heats the air above it through conduction. So at the interface where the very hot ground, the ground that absorbs all this energy from the sun, it heats up, the ground heats up, and then that hot ground is touching the air molecules just above it. And in that way, these air molecules that are just above, the ones that are specifically touching the ground, they are going to get the hot molecules, the hot energy, the heat from the ground, and it's going to heat up those air molecules. And so this first layer of air is going to be hot because it's in contact with the ground, because of the conduction with the ground. Okay, but those particles don't stay there. They undergo another process called convection. So in convection, a group of molecules move from one place to another. They carry their heat energy with them. the red molecules in the picture move upwards. So here we can see a picture of a convection current here and another convection current here. So in these examples, we see that the heat here, right, we have heat from the fire that's heating up the bottom of this beaker. That bottom of the beaker is having conduction with the particles directly above it, but then as soon as those particles have energy, they start to move, and the direction they move is they move upwards. Well, as they move upwards, they create space where colder particles will start to descend. And so in this way, the cold particles, which are more dense, will drop lower into the beaker, or in the atmosphere, the colder air will be also more dense, and so the cold dense air will drop down towards the ground, and the hot air, which has a lower density, will rise upwards. And in this way, the two will switch places, and now these colder molecules will be reaching the ground where, under conduction, they'll become hot again, and they will become the hot particles, which will start to rise up into the air. And then as they rise up into the air, there's less contact with heat. There's not as much of a source of heat because the heat is at the ground level, and so those particles will become cold, and then they will start to descend again. Then they'll heat up and they'll come up, and then they'll cool down and they'll start to descend again. And in this way, they will cycle up and down and up and down. So the red molecules or the hot particles in this picture move upwards, carrying their heat energy to the top with them. The cold molecules move downwards. This is convection. And this is largely driven by density. So these cold molecules are more dense, and the hot particles, where am I going to fit this? Let's put it over here. The hot particles are less dense. And this is also in gases. This is related to pressure. This is how we we can think of the hot air balloon. When we heat up the air in the hot air balloon, it becomes less dense, and that balloon floats up above the colder air particles. But if you turn off the fire that's feeding that balloon, it will start to lose that heat, and it will cool down, and as it cools down, the air inside the balloon becomes more dense, and the balloon reduces in size again, and the balloon falls to the ground. Convection is important in the study of weather because once the ground warms the air directly above it, the air will rise, taking the heat energy with it and helping to heat more of the atmosphere through convection. In your home, convection is incredibly important. This is why you have why many houses are equipped with with hot air ducts that blow hot air in. You may even notice that in many houses you'll have a hot air duct right in front of the window, right underneath every window, and in this way it will move hot air up where the cold windows in the winter would normally cool the air, so there aren't as many differences in temperature across your house. And we actually will move the air around our house purposely using that sort of convection. So in your house you have a vent. It pumps out hot air, and then that hot air will cool eventually, cools, and drops back down, and that's usually where you have a cold air return, where it will be sucked into your furnace, and which has flame in it, and then it'll be heated up and pumped out again. So we have that's how your house kind of heats itself. Okay, my wife worked in heating and ventilation, so I had a lot of talks about how hot air moves around your house. Okay, so let's talk about radiation, the last type of heat transfer that we're going to talk about in this course, or in this unit, or at least in this lesson. And so in radiation, the moving particles in a warm object create waves that send the energy to another object. The waves hit the other object, and the energy is given to the molecules in this new object, making it warmer. The energy travels by waves, not by molecules. So this is a concept that we won't really come back to until a physics course or a chemistry course in grade 11 or grade 12. And in those courses, we'll talk a little bit more about what is electromagnetic radiation, what does this mean by it travels by waves. But in this way, we can think about it that we're talking about light. Light is a radiation, and different types of light carry different amounts of energy, and that energy travels with or without a medium. You don't need anything in between for radiation to travel. Radiation can travel through the vacuum of space because even though there are no particles in convection. Remember that convection, the particles carry the heat. In radiation, the energy travels without particles. In terms of weather, radiation is important because that's how energy from the sun is able to reach the Earth. There are very few particles in outer space, so heat from the sun cannot travel anywhere by means of conduction or convection. In fact, the sun itself has a whole bunch of convection and conduction happening in it, but that is all contained inside the sun. And those processes where there are these sort of nuclear explosions essentially happening inside the sun, they create these radiation waves that then can travel through space and hit the planet. However, it is not only the sun that emits radiation. Particles in all objects can emit radiation. The type of radiation depends on the temperature of the particles. So and we all probably have one of these in our houses, we have a microwave. A microwave has molecules in it that are disturbed by the electrical current from your plug, and then they will be excited in a certain way, and then they will emit these waves, these microwaves, and those microwaves can be absorbed by the molecules in your food, specifically water. Those molecules in your food, those water molecules in the food can then conduct that extra energy they have to the other particles in the food and cook it. And that's why something with lots of water can cook very fast. So if you ever put chicken or cooked noodles or in your microwave, you'll find they heat up very fast. Take something that's a little drier, like even a very thinking about something that cooks slowly in a microwave, a lot of water. Any that has too much water or too much mass or is very dry, the microwave very well at all. So if you get some real dry toast and put it in the microwave, you probably will notice that it doesn't heat up as well as something that has a little bit of water in it. Anyways, that's because of radiation. The molecules absorb the energy from the radiation, and then they can emit that energy again in different ways. So, for example, this picture of an elephant is taken with an infrared camera. An infrared camera detects those radiation waves that are coming off of that elephant. And there'll be more infrared waves coming from hotter areas on the camel and less from the cold parts. So the coolest part of an elephant is its ears, where it actually uses some convection. It moves the ears back and forth to move air around, and it pushes its blood through its ears to cool that blood down. That's one of the ways it can cool itself in the hot air. So heat flows by conduction, convection, or radiation. Radiation is the only one that can occur without particles in between. Convection, the particles are in motion and they are mixing, and conduction, there's no mixing, but the two particles are in contact. So maybe let's put a little bit of a summary here to just put that in words. So conduction, in terms of conduction, the particles are not moving. Particles don't mix, only in contact. In convection, the particles are mixing, And in radiation, there are no particles. There are no particles, there is no particles, or no contact between particles, maybe. Move that down here so you can kind of see it. No contact between particles. Okay, so I'm going to post these questions up again as a quick quiz, so you can check that out online, and we will talk to you in the next video later. Have a great day.